Dear students, we have got a brief introduction to the branch of statistical mechanics. Now, before we go to the details of the subject, let me give a quick recap of what we have discussed so far. We have seen that the statistical mechanics aims at studying the macroscopic properties of a system using the knowledge of the microscopic properties of its constituent particles by using the laws of mechanics. It predicts how the overall behavior of a system of many particles is related to the properties of the individual particles. So in a way we can say that statistical mechanics is nothing but statistics with principles of mechanics. It's concerned with what is most likely to happen than the actual motions of the individual particles. It do not give the life history of each individual particle in a system, but give us the probability that a particular particle has a certain amount of energy at a certain moment. It's quite useful when the system has got great many number of particles, like gaseous system, free electrons in metals, or studying the properties of stellar systems, the future of stars, whether it will end up as a white dwarf or as a neutron star, and like that. It deals with how the total energy is distributed among the particles of a given system. And remember, statistical mechanics is applicable to classical systems like molecules in a gas and quantum mechanical systems like photons in a cavity, free electrons in a metal, etc. And that is the reason why we have concluded that statistical mechanics is one of the most powerful tools in physics. So that was a quick recap of the fundamentals, the aims and the methods of statistical mechanics. Now, in this session, we will be discussing about the concept of microstates and macrostates in statistical mechanics and how the entropy is related to probability. To be very clear, the thermodynamic probability. So the aim of this session is to have an intuitive idea regarding the famous Boltzmann's relation on entropy. How the equation S equal to K log W or K log omega is arrived at. What are the bases? So we'll spend a little bit of time to understand the basics of all those equations. So in the preliminary discussions during the first module in thermal physics, we have seen that there are 2 points of view in studying a system. One is known as the macroscopic point of view, where we focus on the bulk properties of the system, and the other one is known as the microscopic point of view, where we bother about the molecular level or atomic level properties of the system. So corresponding to these 2 views of the system, we define 2 terms, especially in statistical mechanics. In the statistical analysis of a system, we define 2 important concepts, what are known as the macrostate, or to be very precise, it is actually the short form of macroscopic state, and the other one is known as microstate, or it's also known as the microscopic state. So the abbreviated form, the most common form, is known as microstate. Now, in the macroscopic, macro means big, or bulk. In the macroscopic point of view, the macrostate of a system can be defined as the state of a system which is described in terms of the measurable bulk properties. What are the measurable bulk properties? The measurable bulk properties include volume of the system, number of particles of the system, the total energy available to the system, the temperature of the system, etc. So if we are describing the state of a system, okay, if we are describing the thermodynamic state of a system by specifying its bulk properties, directly measurable properties or gross properties of the system, then that state description is what is known as the macro state of the system. For example, we usually denote the macro state of a system by specifying the number of particles in the system, the total volume available to the system, and the total energy of the system. So by labeling these parameters, we are actually referring to the bulk state of the system. So when you specify the bulk state of the system in terms of such gross properties of the system, we do not know what actually is happening at the molecular level. Suppose that there are some million particles in a system, in a cubical box. Okay, 1 centimeter cube volume. You have got a cubical box, and you have say that some 1 mole of a gas is there, okay. So Avogadro number of particles are there in the particular box, and suppose that the total energy given to the system is, say, 10 joule of energy is given to the system. So when I say only this much details about the system, what all things I have specified, I now know how many particles are there in my box, which is my system, okay, in the container. The number of particles is known to me. The volume available to these particles is known to me, that is a cubical box of 1 centimeter side, and also what is the total energy that is shared amongst these Avogadro number of particles is also known to me. Okay, then I will say that this particular description is denoting the macro state of the system. So in the macroscopic description of the state of the system, I know only the bulk properties. Okay, specifying the bulk properties of any system in terms of the measurable quantity is what is known as macro state. So there are several ways in which you can describe the macro state of the system. So they are they can be specified in terms of the number of particles, volume, and energy, or they can be described in terms of the temperature, the volume, and the number of particles, or it can be in terms of some other properties like chemical potential, the volume, etc. So there are several ways in which you can just specify the macroscopic state of the system. Okay, just sorry for the disturbances. Okay, then we will go to what is known as the other description, what is known as the microstate of the system. By microstate of the system, I told you it is representing the microscopic state of the system. Okay, so in the macroscopic description of the system, we do not know how this particular amount of energy is distributed amongst the n particles of the system. You only know that there are some 10 joule of energy and there are some fixed number of particles. You do not know how this total energy given to the system is shared amongst the members of the system. Means how this energy is microscopically distributed amongst the members of the system. We do not have any information at all. We only know the bulk, that this much is there, this much number of particles is there, volume is there. So if you are able to predict what will be the distribution of this energy, you please note the word distribution. Okay, and this is where the 3 distribution functions has derived its name. The distribution of energy amongst the members of the system. Then you will be able to make better predictions regarding the behavior of the system as a whole. Okay, and the thermodynamics was basically studying the macroscopic properties of the system. That's why we say that thermodynamics is nothing but an observational method of studying a system. So we need to observe only the bulk properties like pressure, volume, temperature, etc. We were not bothered about how these properties are originating. Okay, only in the kinetic theory of gases, at least we went to investigate how pressure was related to the motion of individual molecules. Okay, nowhere else. Okay, we were least bothered about how these properties were arising out. Okay, so remember the distribution of the total energy of a given system amongst the individual particles of the system gives you an information about what is known as the microstate of the system. And how do we specify the microstate of the system? Usually we specify the microstate of the system by specifying the position and momenta. In terms of mechanics, the complete description of a system can be done if we are able to specify both position as well as momenta. For example, if a particle is moving in one dimension along x-axis, just you specify x and px. You specify x and px, its complete information. If the particle is moving along 3 dimensions, then you have to specify x, y, z, its position coordinates, and its corresponding momentum coordinates. What are those? The px, py, and pz. Okay, so if we are able to specify the position and momenta of each of the constituent particles, for example, suppose that there is 1 mole of a gas in a enclosure, you have to specify the position coordinates of each of these Avogadro number of particles. It's quite a tedious process actually. It's easy to say rather than to actually measure. But in principle, if we are able to specify the position and momenta of each of the constant particles of the system, then we can say that we know the microstate of the system, at least in principle. So the microstate of a system gives a complete microscopic description of the system, complete molecular level description of the system. If we are able to give a complete molecular level description of the system, we say that we know the microstate of the system. Okay. Also, this microstate is known in other names. It's also known as the quantum state. So I told you that the statistical mechanics can be considered as a forerunner of quantum mechanics, and you are about to study quantum mechanics in the next semester. So where you will see that, or at least you have learned that, corresponding to the state of a system, there is what is known as a wave function. In chemistry classes, at least you have learned about the Greek letter psi, is wrong, and psi is actually represented as a function of r and p, the position and momentum usually, or x, y, z, px, py, pz. There are different ways. Okay, maybe it can depend on time. That is known as time dependent wave function. So this wave function is representing the microstate of the system. So it is also known as quantum state in quantum mechanics. So in the next semester, when you learn about quantum state or wave function representation of state of a system, you remember that the quantum state, which is also known as the eigenstate, we'll say eigenstate. These are all related terms. So that represents what is known as the microstate. And Boltzmann, who is regarded as the pioneer in all these terminologies, Boltzmann actually preferred to call the microstate of the system by what is known as complexion of the system. What's my complexion, right? Complexion of the system means different appearance. Complexion here means what? A system can manifest or appear in different forms, and each manifestation of the particular system. So the gross properties of the system remains the same, but it can appear in different attires, different dress, like I can say. So each complexion of the system can be regarded as what? One microstate of the system, right? And or you can say that each distinct arrangement of a system is known as a microstate. I know that there is a little bit of ambiguity maybe there in my definitions and all. I'll make these concepts clear more and more in the coming examples. So you try to understand one thing, that macrostate refers to the description of any system in terms of the gross or bulk measurable properties, where we do not know anything about what is the type of distribution that has happened in the molecular level, but that is sometimes not sufficient. A macroscopic description may not be sufficient in the complete description of the system in all cases. So we prefer another type of description, what is known as the microscopic description, where we have to know the molecular level molecular level distribution of energy given to a system. and that is possible if we are able to represent in principle the position and momentum of each of the particles in a given physical system. Okay, and we will see that the number of microstates a system can attain, which is known as accessible microstates. There is a word that we will be using repeatedly, that is known as accessible microstates. Accessible microstates. Like there are some microstates which are not accessible. We can define such microstates which are not accessible, and we physically what is relevant is only those microstates which are what accessible to the system. We'll understand what is meaning of accessible microstate. And one more point before we go to the description of what is meant by microstate and macrostate. See, for a given macrostate, means corresponding to a given macrostate, there may exist a large number of microstates. Corresponding to a given macrostate, there may exist a large number of microstates. You keep this sentence in your mind, and I'll be able to explain this sentence in the coming slides. Okay, so I can give you a very straightforward analogy for these things. For example, if you are if you want to describe, if somebody wants to describe third DC physics, say, remember this is not a physical example, this is just an analogy. Okay, only I want to give you the concept. You convert all these things to the system. So suppose that my system is third DC physics 2018 admission. Third DC physics, okay, means your batch. Let me say that this is my system, this is my physical system. Okay, and a macroscopic description of the system would be like this. See what I can do, I can specify that there are 29 number of students. There are total strength of the student is 29. Okay, or if you want, I can specify there are this many number of boys, this many number of girls. Even if I do that, that is more microscopic. So let me say that there are 29 number of students, okay, in the class. Like, okay, and if on a particular day, suppose that out of this 29, suppose that there are two are absent. I'm writing strength 29, absent is 2. Absent is 2. Okay, so suppose that I just write this much, and usually we find such tag on in the schools. You used to write it maybe, okay, on the top of the blackboard every day. The class monitor used to write, okay, the strength class. Okay, we'll write class 12th. Okay, even in colleges we follow that, class 12th, strength say 29, and absent is, right? Absent is how many? So say not 2. Maybe in schools it further gives number of boys, number of girls. It depends. Okay, and we just write all these things. Can you see that this particular description? Okay, it gives a teacher or somebody who is visiting your class an overall description of the state of the class on that particular day, right? So it tells you that this is a class, third year physics. There are 29 students in the class as per the nominal roll, and 2 are absent on a particular day. So I can compare. This is something like writing for a physical system that there are this many number of particles. There are this much amount of volume is available to the particle, and say that this much amount of energy is available for the particle. So this is just like writing some parameters, bulk parameters like NVE, okay, or NVT, right? So these are all bulk properties. Similarly, now so that means this is something like so specifying the bulk properties in any format represents the macroscopic description of the system. Now suppose somebody asks you, okay, then in this analogy, what will be the microstate of the system? So the microstate of the system will be giving the molecular level, means individual level description of the system. So how? I can give an example. So the macroscopic description gives only that there are 29 students in the class and 2 are absent. Suppose a teacher wants to know, okay, a teacher wants to know how many boys, how many girls. That is not clear here. Or who all are absent. Whether the two absentees are both are boys, both are girls, or one boy, one girl. We do not have any information from just writing 29 and 2. Right? Clear? Or if there are further, you can see that. If you enter the class, you know, there are number of benches, number of desks. Okay. So, you know that these 27 students who are present can sit in these benches in different ways, right? Maybe all boys, okay, on one side and all girls on the other row, right? Or, okay, so it's mixed. Or, see, the front two benches are empty and all other benches are what, full, as what usually happens, right? So, there are number of permutations and combinations in which these students can arrange themselves inside the class. So, this is what we call as distribution. How the individual particles of a system is distributing themselves within the accessible macro state, within the permitted variables N, V and E. That also is what is known as what? Different complexion. So I can say that each, that is why I have given a sentence here, each distinct arrangement of a system, can be regarded as a microstate. So I can say that for example you have got, okay, so I will try to give you, because this is a very fundamental concept, I want to give you some clarity. Suppose that this is our system. You have got the box of gas that I described. Suppose that there are only 10 particles. See, I should not talk about a system with 10 particles using statistical mechanics, because that is not going to give me anything that is correct. Because I told you that the statistical mechanics predictions will be giving you meaningful results only if the particle number is very high, right? Otherwise the statistics will fail to give you accurate results. But take this one just as a toy model. Take this one as just as a toy model, because I want to give you a very simplified idea regarding a very complicated system. So consider that I have only 10 particles here. So now see the 10 particles I'm just representing inside this one by some, okay, no, certain 10 dots. It can be anywhere in the box, right? And suppose that there are 10 joules of energy that is shared by 10 particles. What all things are possible? The possibilities are like this. See that the single particle is taking the entire 10 joules of energy, and the remaining 9 particles are having 0 energy. That's possible. That's a possibility. Is right? Even though it is not the most probable distribution, right? Or it can so happen that 5 joule of energy is shared by 2 of the particles, and the rest of the 8 particles have got 0 joules of energy, right? Or it can also happen that 1 joule of energy has been shared by all the 10 particles equally, right? That's also a probable distribution. Now, each of this distribution is a distinct arrangement, and each of this distribution, each of this state is what is known as a microstate. But never ever this 10 particles will all together have 11 joule of energy. Is it clear? Never ever these 10 particles all together will have 11 joule of energy. Why? Because we already know that the macro state of the system is that 10 joule of energy, 10 particles, and maybe say 1 centimeter cube of volume available. So the permitted energy is only 10 joule. So how can the total energy be 11 joule? So such 11 joule, okay, such a type of microstate will never be there. Okay, so all different possibilities, that's what we have to understand. All different possibilities is what is known as what? Microstate. The different possibilities or the different distinct arrangement that a system can have at the molecular level corresponds to what is known as an accessible microstate of the system, right? And for a given macrostate, that's why I told you, for a given macrostate there can be a large number of microstates, and we will see that greater the number of microstates, greater will be the probability that the system will be in a stable configuration. Or I can say a state or a system will always tend towards a macrostate having maximum number of microstates. A system will be always having a tendency to move from one macrostate to another macrostate. And what is deciding the direction of this movement? It will be trying to move from a macrostate having lesser number of microstate to a macrostate having larger number of microstate. So there is something that is important in the counting of microstates. So what is important in statistical mechanics is corresponding to every physical system, you should be able to predict or count statistically or mathematically what are the accessible number of microstates of the system. And the total number of accessible microstates of a system is what is represented by the letter W in the famous Boltzmann's equation for entropy. S is equal to K or KB log omega, the famous Boltzmann's equation for entropy. This W, which was seen, or instead of W, this letter omega is also used. Different symbols are used, or this particular gamma, capital gamma, Greek letters are used. All these symbols are used for this particular quantity, and this W represents the total number of accessible microstates for a system. And it's also known as thermodynamic probability. Omega is also known as thermodynamic probability, but remember that this thermodynamic probability is not our actual probability in statistics. Okay, because the maximum value of probability in statistics is what? 1, you know. Is it not? Okay, probability. Mathematically, the total sum over R, PR, that is the way in which we write, that is equal to 1. Total probability should be equal to 1 for a complete event. But this W, even though it is named as thermodynamic probability, remember it is representing the total number of accessible microstates for a particular system. And I think coming 2 or 3 sessions, I will be able to give you more physical idea regarding how this particular equation is derived and what is the relevance. And in next session, I will give you some example of how to count the number of microstates. So let me conclude the session like this. The main target or the main issue, okay, the main aim of statistical mechanics is to find out or to count the number of accessible microstates for the given system. And from knowing the number of microstates, you can use the Boltzmann's relation for entropy, and you can arrive at what the value of entropy of the system. And once you get the entropy of the system, by using the Maxwell's relationships, which relates entropy with other parameters, you will be able to get what? All other measurable parameters of the system. And that is simply the technique of statistical mechanics. Thank you.